Hi everyone, welcome to Introductory Python Tutorials, where we are putting special focus on image processing. And we are in the middle of our discussions or our learning process of semantic segmentation using units. And in the last video, we talked about binary semantic segmentation, where you only have the background and the foreground. In the previous example, it was background and mitochondria. And the activation function in the output layer was sigmoid. For binary, always think of sigmoid. For multiclass, always think of softmax. That's exactly what we are going to change in this video. So here we're going to focus on basically using the same unit network that we built a couple of tutorials ago, and then we used it in the last video for binary, and in this one we're going to use it for multiclass. And what are we going to change? We're going to change something to reflect the actual use case here, which is I have a data set that has multiple features of interest, and this can be useful for satellite images and even for MRI, like Brad's data set, if you would like to segment that. Although for that you need a 3D, and we'll cover that later, 3D unit. But for now, let's focus on multi-class. We have many classes, not just binary. What do we mean by that? Well, you have one class right there, which is pretty much everywhere. That's our majority class, and it's easy to classify. And you have another dark region all around. That's also easy to classify, majority class. You have the bright regions here. They're minority class, but also easy to classify because they're so bright. It's very easy. You can use a histogram to segment those. And finally, you have these regions that are tough to classify. We used exactly the same example for our random forest. Yeah, when we did traditional machine learning. And the data set is available. I'll share the link where you can download this so you can practice it. But you can practice on any other data set. What are we going to change when it comes to multi-class semantic segmentation? So here you see the final layer, conv2d 1. We're going to change that to, in our case, we have 4 classes. We're going to change that to 4. So it gives us 4 outputs. Think of what the implications are by changing that to 4. If your input image is, 256 by 256 by 1, your output here is going to have 4, not 1, which means it's a 4-channel image. And in each channel, it's going to have a probability value for that pixel, for that channel, to be the primary channel. Okay? For example, at each pixel, at that pixel, I have 4 values. If my 0th class corresponds to the gray region, or the yellow in this example, if my 0th class is yellow, then the probability at that 0th channel for yellow is high. And the next one, for red, the probability is low at that pixel. And for the other color and the other color, the probability is low. So we look at which one of these is the winner and assign that to it. So that's what the implications are for multi-class classification. The other thing that you need to care about is the activation function is going to be softmax, because this is multi-class classification. Other than that, nothing changes. Only these two that change. Which means, first of all, we need to change our input masks into a 4-channel mask. Right now, our masks have different values at every pixel. Okay? I need to change that to a 4-channel mask, meaning I need to convert that into categorical. That is what you do from a data handling point of view. But when it comes to the model itself, 2 things: number of classes in the output and activation. So with this knowledge, let's go ahead and jump to the code. Here is the code. Again, as usual, I'll share this on my GitHub, and you can also download the data I'm going to use in this tutorial from this link. And that link contains the data in 2D, different sizes, and also in 3D. So if you would like to use it as part of the 3D unit exercise, which is going to happen in a few tutorials from now, go ahead and download those. Also, if you have your own images and you would like to annotate, meaning you would like to create masks by adding values of 0, 1, 2, 3, right? So you can do these at www.appear.com for free. I mean, this is a free platform. Just go ahead and upload your images. Free platform for academics and nonprofits, I should say. If you're from industry, just talk to us and we can go from there. Okay, so let's go down. These are exactly the same libraries that we imported from the last video. Again, OS and glob to work with our files in the folders, OpenCV to read images, NumPy, and Matplotlib. Nothing new there. In this case, I'm going to work with images of size 128 by 128. I mean, you can work with 256 if you would like to crop with them, but I brought them down to 128 because I have 4 classes and I need the extra, because remember, it's going to convert this into categorical, meaning you are going to have 4 different channels. So if you hit the limit with 256, go down to smaller images, that's all, or smaller batches, either way. So I'm going to work with 128 by 128 images, and number of classes I'm defining as 4. Because that's what we have. And normally, I mean, for this training, I used 1200 total images. But for this demonstration, I'm going to only load 200 images. And we are not going to train the model. I'm going to use those 200 images towards later on testing our trained model. But that's a quick explanation of these variables. And we have done this exact thing in the last video. What have I done? We looked at where the files are, and then we got the image names. Why? Because we want to sort the image names and mask names exactly the same way, so they both match when we line up. And then I'm taking a subset of those images, like 200 of those images, and then reading them right here. So I'll have 200 images right here. A list of 200 images, and then I convert that into NumPy array, expand the dimensions so they have the right structure to go into the neural network. So let's go ahead and run this and the next one. Okay, and by the way, you'll notice that whatever we are doing here is very similar to what we have done in the last video, so I'll speed up a little bit, but again, try not to miss important points here. So let's go ahead and print out our image data shape and mask shape and max pixel value and all that here, okay? So my image data shape is 200 images. We are loading 200 images, and each image is 128 by 128 by 1. My masked data shape is 200 images, 128 by 128, right there, okay? And my maximum pixel value in the image is 255 because we haven't scaled our images yet. And the labels in the mask are 1, 2, 3, 4. By the way, in the previous video, you should probably notice that here we had 200 by whatever, 128 by 128 by 1, both of these matching. I'm not expanding the the dimensions yet because we'll have to do something with our masks. That's why I'm ignoring that for now. We'll get there. So if you look at the labels in the mask are 1, 2, 3, 4. I recommend labels to have 0, 1, 2, 3. Because if you want to use Keras, for example, intersection over union library that calculates intersection over union, it expects the classes to be 0, 1, 2, 3. Also, it's customary to have classes as 0, 1, 2, 3. In fact, in this original data set, I had unlabeled pixels or background as 0. But in this data set, there are no zeros. All we have is 1, 2, 3, 4. So we need to first convert that into 0, 1, 2, 3, and then convert that into categorical. So that's what we are going to do next. So the next step, encode the labels to 0, 1, 2, 3. Yeah. So how do you do that? As part of scikit-learn pre-processing, there is something called label encoder. We're going to use that and instantiate this label encoder and then apply that to our data. But unfortunately, this encoder only works with one-dimensional data, which means I have to take my multi-dimensions like 200, 128, 128, flatten it, meaning convert that into 1D vector, do the encoding, and then bring it back to the same shape. Sounds weird, but that's very common, right? So we are going to reshape that into -1, 1, which means that becomes a one-dimensional vector. And then I'm going to apply label encoder dot fit transform, meaning it's fitting and transforming my data at the same time. What data? The reshaped data. And then we get the encoded vector, that we need to reshape back to NHW, which becomes a vector of 200 by 128 by 128. That's what is happening here. And then let's go ahead and print our unique values just to confirm that we have 0, 1, 2, 3. There you go, 0, 1, 2, 3. Step 1, done. There are many mini lessons in these videos. A lesson about using label encoder, a lesson about doing something else. Yeah. So I hope you're watching this by not forwarding it way too much. I know things can get boring, but I'm just saying that there are gold nuggets hidden in these videos in case you don't know about these, and that's why watching these in their entirety can be very useful. Next step is now I'm expanding the dimensions. Yeah, previously that's exactly what my statement was when I showed you this. Now, okay, I have data that's ready, so let's go ahead and expand the dimensions. So now it is 200, 128, 128, 1. Okay, now I'm happy. Well, we took care of the masks to some extent. We'll still have to do something with that. But our images still have a maximum value of 255 because we haven't scaled, normalized, or min-max scale or nothing. The easiest thing to do, divide your values by 255. So that's what we're doing. So our pixel values all go between 0 to 1. So my input went from unsigned integer 8 with values of 0 to 255 to floating 0 to 1. Okay, that's what that line does. Next. Let's go ahead. In fact, I'm not sure why I changed this to categorical later. I could have done it right here, but fine. Let's follow the flow. Now I have my image and mask, and I know the reason why I'm doing it later because in binary image classification, the steps were very similar. Yeah. So let's go ahead and split the training data: xtrain, xtest, ytrain, ytest. Straightforward. Now is the key part when it comes to multi-class semantic segmentation, because our output, how is our output going to be? We saw that in our presentation earlier. It's going to give me, in this example, an output of 128 by 128 by 4, corresponding to 4 channels. So the y values that go into our model.fit need to be in the same format. So we are converting that into categorical. I talked about this a couple of times in previous videos, but if you don't remember that, from keras.utilities, we are importing to categorical. And then when you provide the number of classes, it converts our 0, 1, 2, 3 automatically into these categorical values right there. So that's exactly what we are trying to do. And then I'm reshaping them into the right format right there. So they are in the right format for our neural network. So that's exactly what we are doing. And in case you wonder what is that right format, let's go ahead and print that, ytrain categorical. And this is, I have 160 images, each 128 by 128. Previously we had 1. Previously we had 1. Previously we had 200 images. But right now we have only 160 images because we said take 20% for testing. So for training, we have 160 images. Previously, we had 128 by 128 by 1. Now we have 128 by 128 by 4. Why 4? Again, because we converted that into categorical. And each channel represents, think of each channel of these 4 as a binary image for each of the classes that we have. That's what that means. Okay, categorical. Now we are going to build our unit. We have done this at least in the last two videos. So the only thing that is going to change is basically actually nothing. We already added this. I was about to say change the number of classes and change the activation, but we have written it such a way that we can do that while calling that function. So let's go ahead and run that. So while calling our build unit, we'll just give number of classes. It automatically takes care of the two things. Putting the number of classes here, also taking the right activation softmax. So let us define our image dimensions and build the model. And I think I'm printing somewhere. I added print statement, like right there, activation. So it prints the activation when we call it down here. So let's go ahead and print it. And one other important thing, when we go up here, first of all, let's confirm that this is using softmax. Obviously, that's what we want. And when you compile this model, use Atom or anything, any optimizer. Loss function, do not use binary cross entropy. It should be categorical cross entropy, or use any other advanced loss functions, but make sure this is not binary cross entropy, because this is again working with categorical data. And metrics, we are tracking accuracy. So if that's the case, let's go down. And again, I trained this for 50 epochs, okay? And what did we get? Not bad. We got about 97% accuracy. What does that mean in terms of intersection over union? That's exactly what we find out when we load the model. I've already saved it after 50 epochs, and we are going to do exactly the same things we did the last video. Model.predict, and oh, sorry, not exactly, but model.predict is exactly what we did in the last video. But when you predict it, this is important. I think you know what I'm going to do here, but just in case, let's go ahead and predict it first. Model.predict. Yeah, and let me delete this line. Here I should have added, let me add another y underscore pred dot shape. Just want to show you that the output is going to be 4 channels, and when you do .argmax, then it's going to be just back to 1 channel. That's all I wanted to show. While this is predicting, I don't know why this is slow today, but let's give it its time. Let us add argmax here. Okay, and then see what the shape is before and after. Okay, so finally that's done. Let's go ahead and look at the shape. So we have 40 images for testing, we know that. 128 by 128, and it gave us 4 channels of output. We need to do argmax. What does argmax do? It looks at whatever the axis we define. In this case, we're defining 0, 1, 2, 3, that axis, and looks at what is the maximum value, and it assigns that maximum value, which is our class. Yeah, so argmax, and look at the shape. After you do that, it's 40 images, 128 by 128. Back to where we started, right? And now of those 40 images, again, I'm calculating the IOU, mean intersection over union. With more images, I got 92%. Let's see what we get this time. Again, we used this function last video. From keras.metrics, import mean IOU, instantiate the mean IOU, and then update the state using whatever the test results that we get here, and the prediction results that we got here, and then the testing data set. So our mean IOU here is 92%. Not bad. I kind of divided that into, if you just do mean IOU, get weights, and reshape this, it actually gives you the mean IOU for each class, almost like a confusion matrix type. So all I did is take that. Sorry for being abstract. Again, this is a place that can be very useful to understand. So there you go. So it gives you the value for the first class, second class, third, and the fourth one, right? So we have like 4 classes, and then all of these are misclassifications. All of these are misclassifications. So all I'm trying to do here, let's delete this. All I'm trying to do here is just do some simple math. We are saying, okay, what is the true values divided by false values? True values by false values. That is my IOU. And I'm printing IOU for each class. Right there. IOU for class 1, 93.7. The class 2 is the tough one. Remember earlier, 20 minutes ago, when we started our video, you saw one of the classes to be the difficult one. That is class number 2 in this case. The class 4 is the bright pixels. I said this is easy to classify. It is, even though I have minority class. Class 3 and class 1 are the majority classes. Class 1 is the silicon that's everywhere, the gray area. Class 3 is the dark area that's also everywhere. Class 2 is the one that looks very similar to class 1, but it has some texture. So this is a tough one to classify. This is how you can use intersection over union information to understand about what's working and what's not working. Okay. Okay, nothing better than visually seeing the results. That's exactly what this part of the code does. So let's go ahead and randomly load a test image and then predict. And that is not bad. That's actually very good, as you can see. And let's run one more time to load a different image. Again, this is even for multi-class classification. You can see how amazing this is, even with 50 epochs. That's it. And I originally trained this with 1200 images, each image 128 by 128. So unit is amazing for semantic segmentation. I mean, you will see some, in fact, I almost said you will see some errors. I can't figure out where it's making a big error between this is the testing label, this is the actual prediction. So it's doing an amazing job, as you can see. So go ahead and test this out. I know most of you either work with binary or multi-class classification, so you have that here that you can already do in 2D. Let's slowly get our way to 3D. Okay, 3D is very easy. You can use exactly the same model that we built, except change your convolution 2D into 3D. And believe me, that's how easy it is to go from 2D to 3D. You can do one 2D slice at a time and then put them together to create your 3D, but then it's not same as having a true 3D convolutional unit. So we'll get there. Again, in the next video, let's extend the knowledge that we have gained right now. Please keep watching these, subscribe to this channel, and hit the like buttons if you really like the content. See you in the next tutorial.